Hello everyone. So in this session, we want to use what we learned in shallow water equations and then solve a real world problem. So I'm just going to tell you how this is being solved numerically. I'm not going to go through too much details, but I just want to kind of lay out the basics and the principles that we learn and how these shallow water equations are kind of used to solve some real world problems. Um, in general, these shallow water equations, because these are nonlinear partial differential equations, so we typically solve them numerically. So here I just gave you some insights about the analytics, but in reality, we typically solve them numerically, especially when we have some complexities, like when we want to do routing or we want to find like the stream flow rate or the channel or river stage and these kind of things. So let's get started. So imagine we have this flow that is moving over this over some slope. Okay, so we have some this water. It could be a river or a channel that is moving over this some slope, some kind of a gentle slope, and then it has some velocity u bar, which is kind of the depth average velocity. We have also the depth of that, which is shown as h, which is a function of x and time. So this is just a one-dimensional flow. It can be, you can generalize it to two dimensions. So it can also have a width in the y direction. But here I'm just showing the simplest case for you. And then this water, because it's kind of on top of soil, it has also some infiltration into the soil that is shown with IXT here. Okay, and also imagine we have some rain. We can have some sporadic or like a random rain that kind of adds some water to this channel, and we show this rainfall with r, x, and t. At position x and at time t, we can have some source of water to rain to this channel or river. So we want to solve these equations and we want to see how the water depth and stream flow, its velocity changes with time. So in order to do so, we can use shallow water equations. So first one is continuity. So the continuity equation for shallow waters, I can write it as partial h over partial t plus partial h u bar over partial x. And now it doesn't equal to 0 because we also have some sources and some sinks. So the sources of a mass or mass flux is rain. So I'm going to show it with R, which kind of adds to this to the contour volume. And then we also have some sinks through infiltration, which I show it as I. So R, or rain, is the source, and I is sink. Okay. And also we can write momentum equation for these shallow water equations that we already derived, right? So I'm gonna use this form of that, okay? But I wanna bring that to the left, so I will bring this to the left, the right one to the left, and then I will just write it as this. So we have partial h u bar in the conservative form over partial t plus partial over partial x of hu bar square plus gh square over 2 okay? And this equals to 0 if we don't have any viscous forces. And also here, just remember this equation that we derived here, or this momentum equation, was when we didn't have any gravitational force in the x direction, right? So we assume we don't have any gravitational force in the x direction, like here, right? Because this one we assume that the flow is moving horizontally, so there is no there is no gravitational force. So the gravitational force, which is completely in the z direction, so there is no gravitational force component in the direction of the flow, right? However, here that now we have, and also there is no viscous forces. That's why we use Euler's equation. So we use Euler's equation here. Yeah. And we assume, because we assume that there is no viscosity. But in real world cases, we might have some viscous forces as well. And also here, because, let's see. And because we have, see if I can get this. Yeah. And because we have also because we also have because we have some slope, the gravity might also help to accelerate the flow in the x direction. Okay, so we have two additional forces here. One is due to gravity, so I'm going to write 1 over rho of the weight of the fluid, so weight in the x direction. And also we have the viscous forces that might decelerate the flow, so in reality in the x direction. Okay, so this is going to be my two equations that I need to solve in order to find the real world, the depth and velocity of the fluid. So let's first investigate the gravitational force. So say here we have Fw, the weight of the fluid here. So let me say we have the weight of the fluid. And this is let me move this. So this is the weight. And then say this is a gentle slope. So here we have theta. This is the angle. So this angle is also theta. It's perpendicular to this. Okay. And this direction is z, this is x, and so the term of the gravitational force that accelerates the flow, which is Fw, let's say in the stream flow direction, or x, is just, let me just write it, FW. Here, this one is going to be FW times sine of theta, this component that is kind of accelerating the flow. Okay, so this has to go to the momentum equation in the stream flow direction. And because I can assume a gentle slope, so like the slope is not too much, so if theta is small, we can assume that sine theta is almost equal to tangent of theta. Okay, and what is the tangent of theta here? You can say it is partial z over partial x, right? So here you have it. Let me maybe a little bit bring it here. So this is theta. So this is like partial z. This is partial x, right? So tangent of theta is going to be about partial z over partial x. So 1 over this term, 1 over rho F weight in the direction of the stream flow is gonna be what? So instead of FW, what is FW? FW is the weight of the fluid. Okay, so I can just write it as rho times its volume. So the volume is h times a cross section, say the width of the fluid, which is W, and then times G. But here, this term that is here is already divided by W, so we already have canceled out that term from all the equations. So we only have rho Hg. So 1 over rho F weight of x is gonna be GH times sine of theta. So sine of theta is just partial z over partial x, right? So let me write it this way again. So it's going to be GH times sine of theta, which equals to about tangent of theta. So I can write it as GH partial z over partial x. And sorry, one more thing is this is minus partial z over partial x. Right? Because partial z, in this case, partial z over partial x is actually decreasing. So z is actually decreasing. So this has to be the sine of theta is a positive number here, right? But partial z over partial x, because z is kind of decreasing, is a negative number. The slope with respect to z is negative. So the tangent of theta should be if this is partial x, so let me write it this way. This has to be minus partial z partial x, right? So here this gh sine theta is correct, and here we have a minus sign here. And so this will give me minus gh partial z over partial x. Again, just to say it again, so if this is x and z, so this slope is negative, like this partial z over partial x is negative, right? But the theta, the sine theta, is a positive. So the actual one, the tangent of theta, is going to be minus this. Okay. Okay. So now let's go to the second force, which is viscous force. So F viscous and X. For this force, we typically use an empirical relation. So we don't, for these kind of hydrological applications, they typically use empirical relation for velocity. Okay. Because this is a kind of a specific problem. It's just for these channels. We typically use empirical relation, which I think you know it from your undergrad fluid mechanics or hydraulic engineering course, which is known as Manning's equation. So Manning's equation states that, say, if you have a channel which is filled with water, it's an empirical relation, meaning it's just they have found it by fitting some curves. So they measured the velocity, and then they found this relation for the velocity in a channel, which is phi over n hydraulic radius RH to power 2/3 times SF square root of SF. So let's see what are these. So this is an empirical relation. So phi here is 1 if you are using a metric units, or it's going to be 1.486 if you are using English or British system. Okay. So in SI units, this phi is just 1 if you use SI units. Okay. And what is RH? So RH is hydraulic radius. It's just the area of that channel over the weathered perimeter. What is weathered perimeter? Weathered perimeter is the how much of that channel is wet. So this is going to be here. This is P, which is wetted perimeter. So radius, and the area is just this, right? So the area is going to be the area of the channel which is this. So this is the area. Okay, so A over P, this is going to be hydraulic radius, so you just put it there. What is N? N depends on the roughness, and it's just Manning's N. They call it Manning's N. Depends on the roughness of the channel or the river. So for example, if you have a concrete channel, N is gonna be 0.012. If you have a gravel channel, which is rougher, your N is gonna be higher, so it's 0.025. Okay. So this is the relation for this Manning's equation, which is kind of a empirical equation. And SF is just friction slope, which I'm gonna talk about it. So now we have this force, this 1 over rho of F viscous is gonna be, so we can write this in terms of the wall shear stress, okay? And then use this friction, surface friction from this Manning's equation to get it, okay? So this is what we typically do. So in terms of shear stress, this is going to be minus tau times P, which is a weathered perimeter, over density rho times A times H. Okay, so this is going to be the formula, and this is just wall shear stress. Okay, so it's just integrated. You just integrate the wall shear stress, and then this is what you are going to get in terms of the viscous force. So this is going to be your viscous force, okay? And SF, which is the friction slope, is tau, your wall shear stress, over rho g A over P. Okay, so this is another relation that we have. So now we can combine these two equations together to get the viscous force in our problem. So in general, the viscous force, the way we show it is, so here, for example, instead of tau, we can write minus, I'm gonna write it rho g A over P from this relation times SF over rho A H sorry, the H should be here, and then we also have P. Okay, so now these terms are gonna all cancel out. So this P is gonna cancel out, this rho G is gonna, sorry, we don't have G at the denominator, so we only have rho. I just write it from here, right? So this rho is gonna cancel out, This A is gonna also cancel out. So what I'm left with is minus GHSF. So in other words, in a simpler way to show it is that this viscous forces is we just multiply GH times this friction slope, right? So then this friction slope is gonna give us how much friction we have in the system. And for friction, I'm going to use Manning's equation from here. So let's see what it was. So this is Manning's equation. So use Manning's. So we are gonna get U bar square from Manning times N square over RH to 2/3, and assume that phi is 1. Is 4/3, sorry. So 4 over 3. Okay, so this is from Manning, and then this is gonna be my friction force. Okay, so I have everything now in terms of U bar and the channel characteristics, right? So if I want to solve the equation, the routing of this channel, if this river or any channel, I can just use these equations that I have. So I want to write them in terms of matrix. So this is how we are gonna solve this. So the first term, these two equations numerically. So the first one, let me put it here, is partial h over partial t equals to r minus I. So let me write this down. So we have h here. Then we have partial over partial x. Of HU bar equals to R minus I, right? So to the right hand side, R, which is rainfall minus infiltration. So this is continuity. And then the second equation I have is this HU bar, partial over partial T of HU bar. And then, so this is plus. So this is HU bar, partial HU bar over partial T. And then plus partial over partial X of HU bar plus 1/2 GH squared. So this is the left hand side, and then what is the right hand side? So the right hand side is this. This is the right hand side. So I have 1 over rho of F weight plus F viscous. Let's see what is F weight. So F weight, we got it here. So it's just minus GH partial Z over partial X. So minus GH partial Z over partial X. And what is F viscous? F viscous is going to be minus GH SF. And what is SF? SF is here, so I can just write it down. Plus U bar square N square over RH4 third. And now the equations are closed. So this is a very general formula, and if you want, you can just write a code to numerically solve this for different conditions. For example, when you have rainfall and when you have infiltration, when you don't have any rainfall in infiltration, so then this term just becomes 0, right? And then when you have slope, like partial z over partial x is your slope, or when you don't have any slope. And in terms of different roughnesses, like when you have a concrete or different type of channels, so RH hydraulic radius, again from your undergrad you can go and look. For example, if you have a rectangular channel or a circular channel, this hydraulic radius might change also depending on how much the water is filled is going to be different, right? So you can just have a lot of different conditions, and so this is the governing equation for that. So the governing shallow water equations, or governing shallow water equations for a general, in a general form, let's say. And so you can write a code. It's hard now to solve this analytically, so because you have a lot of things, especially on the right hand side, it's not as easy as before. We have a lot of forces like the gravitational force and friction force, as well as sources and sinks. So it's better to solve this numerically with the help of computers, so you can just write a code to solve these together. And your unknowns are h and u bar. So you can solve this and finally get a solution in terms of time and space for h and u bar. So as you go, you can just integrate this with respect to time at from time 0 to time, say, n, and then at different locations you're going to get the shape of the depth of the water, as well as your u bar, or the velocity of the water. Okay, so this is actually the way most of hydrological models work. So these are actually the governing equations for these models. They just use this equation that is shown here, okay, and then they solve this in time based on the conditions that you give to them. Okay, for example, I think HECRAS and a lot of other things, like in wharf routing, for hydro routing, they all use these shallow water equations because these are very simple, much simpler form of momentum and continuity equation in general, and these are just by using the shallow water assumptions. Okay. So this makes the flow much simpler. Okay, so in this session, again, just to have a recap, we started with rescaling these shallow water equations. So we got a simpler form of that, which is shown here. And then we found the characteristic curves of this. And using this characteristic method, we can gain some insights into the analytics of this. So this is a hyperbolic formula, meaning that we have two waves. One wave that, depending on the flow, if the flow is subcritical, will move to the left-hand side, and one wave which is going to travel to the right. And if it is critical, we only have one wave that is going to just move to the right. And if it is supercritical, we will have two waves that are going to move to the right at the same time. Just remember, sometimes they call this part zone of dependence. I said zone of influence in the previous session, but also they call sometimes this part as zone of dependence, meaning whatever happens here, depending on that, this is just a convention in different fields. So, for example, whatever happens in the past in this region is gonna influence P. So the P is dependent on this region, and whatever happens in the future in this region depends on P, point P here. So P is gonna influence that region, okay? So these are just some conventions, the way that they name these regions. And then we talked about the surface overland flow, a general formula for solving these shallow water equations. So what we added was two forces. One was the gravitational force and one was viscous force. So we added both of these forces as well as sink and source terms in the continuity equation due to rain and infiltration. So we got this general formula, which is actually the governing shallow water equations in a general form that is being used to solve this equation numerically in many software. Okay, thank you very much, everyone. So in the next lecture, I'm going to start talking about a general form of momentum equation, which is Navier-Stokes equation, which we account for viscous forces as well.